Hi guys! Today we're going to be talking about mechanical energy and a little bit about work. So we're going to be talking about what is mechanical energy, what do we mean by that, how do we calculate mechanical energy, how do we calculate other kinds of energy, and what counts as work according to physics. Let's get started. So, first thing we should know is that energy is conserved. It's never created, it's never destroyed. The amount of energy in the universe is static. It's going to change between different kinds of energy, but the total amount of energy is going to stay pretty much the same. There's different forms of energy, different kinds of energy, and you can see those listed off on the right. We've got light, heat, motion, sound, electricity, and chemical energy. Chemical energy is what we talk about in chemistry, and we're not going to talk about that very much in physics. Heat is what we talk about a little bit later. So this unit is primarily dedicated to motion, energy of motion. And what is energy? Energy allows objects to do work, and we'll describe what work is in a little bit. And the main kinds of energy that we're going to be talking about are kinetic energy, which is energy of motion. And remember, anything that kind of starts with a K-I-N-E-T, like kinesthetic, kinetic, kinematics. Kinematics were the equations that we used for accelerating objects. Kinesthetic is a kind of learner who learns with their hands. So kinetic energy is energy of motion. And the other kind of energy we'll talk about is potential energy, which is energy that is stored. And most of our storage comes from changing position. So it's kind of like an energy because of an object's position. And all of our kinds of energies in physics are going to be measured in joules. Joules. That's named after a scientist who pioneered energy-related physics, and it is abbreviated with a capital J. In other units for energy, we have calories, which you often see on foods and nutrition labels. So, what is mechanical energy? Mechanical energy is not a kind of energy itself. It is a group of other kinds of energy, specifically these three, and only these three: kinetic energy, gravitational potential energy, and elastic potential energy. Only those three energies make up mechanical energy. And my notation may be a little different from some other notations that you see. I usually use E for energy with a little subscript as a label for which kind of energy it is. But for kinetic energy, you might see capital K or capital KE. For gravitational potential energy, you might see P, capital PE, or even capital GPE. Or if you're in a university setting, you might see capital U with a little g. And then elastic potential energy, you might see SPE for spring potential energy, because it's usually in springs. Or again, if you're in a university, UEL for elastic. And there's several other variations that you might see. It's conserved in most cases, but not in all. It is not conserved when there is friction. when there is friction, mechanical energy is going to be turned into something else. Now take a look at our little roller coaster at the bottom. We have a roller coaster, and right now it's at the very highest position. So over here on our bar graphs, it has maximum potential energy. And since mechanical energy is the total of kinetic, gravitational potential energy, and elastic potential energy, and since our roller coaster has no springs, we can see that the amount of kinetic energy it has plus the amount of potential energy it has is going to equal the total mechanical energy. Now, what happens as our roller coaster goes down the hill? These two bar graphs between kinetic and potential, they switch back and forth. It almost looks like a seesaw. So if it is halfway down the graph, let's put a K, P, M, just for kinetic, potential, and mechanical. If it is now halfway down the ramp, it's going to have half as much potential energy. But where did that energy go? It can't be lost. So it goes into kinetic energy. Our object is moving faster, so it has some kinetic energy. And then the total mechanical energy stays the same. It's going to be constant. If I could animate this, you would notice that the total mechanical energy, that green bar, stays all the way at the top the whole way through the roller coaster. But the kinetic energy and the potential energies fluctuate depending on where our roller coaster is on its track and how fast it's going. So kinetic energy is energy due to an object's motion. The faster it's going, the more kinetic energy it has. Our equation for kinetic energy is 1/2 mv squared. So it's 1/2 the object's mass times its velocity squared. And it's going to be conserved in a perfectly elastic collision. So last unit we were talking about momentum, which was little p, and momentum was always conserved. Momentum is always conserved no matter what kind of collision happens. But kinetic energy is only conserved in a perfectly elastic collision. Now remember, total energy is still always conserved. So if we have an inelastic collision, if we have two objects collide and then stick together so that they're now two objects become the one object, energy is still conserved. It's just not going as fast. And some of the energy got transformed into changing the object's shapes. They were deformed when they hit each other. So some of that energy came from there. Now notice, velocity can be positive or negative, right? Depending on whether it's going left or right, up or down, it can be positive or negative, which meant for us when we were talking about momentum could also be positive or negative depending on the object's velocity. But for kinetic energy, the velocity is squared. So no matter what, kinetic energy is always positive. So the direction doesn't matter for kinetic energy. Potential energy is energy that is stored because of an object's relative to position to some gravitational source. That's a long way of saying it has energy because we lifted it up above the ground or above some certain level. The really neat part about gravitational potential energy is we get to pick where zero potential energy is. It's usually the surface of the Earth, but it doesn't have to be the surface of the Earth depending on our situation or our problem, whatever it is. Spring potential energy or elastic potential energy is due to an object's expanded or compressed position from a spring, right? If we have an object attached to a spring and we move that object away from the spring, we stretch out the spring or we compress the spring, we've changed its position and we've changed the amount of energy stored in the spring. And even chemical potential energy, this is a little neat, even chemical potential energy is due to the position of the atoms or the molecules. That's just a neat fact. So, calculating potential energy, how do we do that? First, we get to pick where zero potential energy needs to be. If we're on the ground, then of course we're going to put potential energy equal to zero on the ground. But if we're on the second or third floor of a school building, then we don't want to have to calculate the height of every floor and figure out how much that is, especially if our objects are not going to fall past the floor that we're on. So we can pick zero potential energy to be up there. So, calculating it, our equation for potential energy, gravitational potential energy, is mgh, which is mass times the acceleration caused by gravity times the height. And remember, little g, the acceleration caused by gravity, is 9.8 meters per second squared. And gravitational potential energy is still energy, so it still has a unit of joules, capital J. Elastic potential energy comes from springs, rubber bands, even your muscles. And how it's calculated is 1/2 kx squared. So k is a new thing. It is the spring constant. So if we have a big K, and this is different from capital K, right? So this is lowercase k, not to be confused with capital K for kinetic energy. But if we have a big number for our spring constant, that means that the spring is stiff. That would be like the shock absorbers in a car, the springs for automatic garage door openers. Those springs are very stiff, so they would have a large spring constant. A small spring constant would mean a loose spring. Loose spring. This is why I don't teach English. That would be like a slinky or some other kind of easily manipulated spring. And we have X again. So X is again for position. Now, it's not the total length of the spring. Notice this picture here, and this picture is from hyperphysics.com. Notice this part here, this part up at the top, that is a relaxed, unstretched spring. So nobody's squashing it, nobody's stretching it, it's just kind of sitting there. That means its potential energy is 0. When it's relaxed, when it's just chilling, it has 0 potential energy. It's only when you stretch the spring away from that position that it has potential energy. And the x that we calculate is only the distance from its relaxed position. Now, one thing I want to mention relates to forces from springs that have been stretched or compressed. So Hooke's law is the law that governs the forces exerted by springs, and it is negative kx. So it's the negative spring constant times the distance the spring is deformed. And the first question we should ask ourselves is, why is there a negative there? So this is the force by the spring. Okay, so let's draw a little spring. Spring, spring, spring. If we pull the spring this way, if we pull the spring out, usually pulling a spring out is considered positive. Which way is the spring going to pull on us? The spring is going to want to pull us back. So that's negative. So anytime we pull positive, the spring will pull negative, right? So we need that negative there. If we want the force that we need to exert, so force needed, that would be equal to just kx. So if we want to pull the spring out in a positive direction, our force also has to be out in the positive direction. So depending on what you're being asked, it might be positive, it might be negative. And just be aware that if we compress the spring, if we squish it in, that's considered negative, right? So this would be a negative x displacement, because position is always a vector. It can be positive or negative. If we push it in, the spring is going to try to push us back out. So the force of the spring is going to be in the positive direction now. So it flips when we're talking about the force of the spring. Now, another thing to realize is that this is not a constant force. Let me erase this. So the acceleration is not constant. If we don't have, that's part of Newton's second law. Remember, force equals mass times acceleration. So if the force is not constant, which it's not here, right? We have a variable. The x can change. Spring constant is fixed because it depends on the spring, but the x can change, so our force can change. And if our force changes, that also means our acceleration is changing. Whenever acceleration is not constant, our Cinderella equations, these 5 equations over here, right? Cinderella, Prince Charming, and the 2 ugly stepsisters, they cannot be used. We can't use those if we have our object touching a spring. Whenever a spring is touching our object, we cannot use those Cinderella equations. So let's do some comparisons between the kinetic energy, potential energy, and spring potential energy. So what happens if we double the mass in the kinetic energy? So we have initially 1/2 mv squared, but we are trying to double the mass. So we go like that. Now remember, multiplication, the order that you do multiplication in does not matter. If you multiply 2 times 3, that's 6. If you multiply 3 times 2, that's also 6. So we're going to shift around our things. Our new number is right here. So we're going to move that to the side and just leave all of our other numbers that we originally had. 1/2 mv squared. This is the same as what we had up here. So what have we done to it? We have also doubled the kinetic energy. So if we double the mass of an object that's moving, we also double its kinetic energy. Okay, so what about doubling the velocity? Are we also going to double the kinetic energy? Not this time. We have to be very careful because look, we have a square up here. So what do? Same thing. 1/2 m, but this time we have to square the entire doubled velocity. So we're doubling the velocity, but we have to square all of that velocity. We're not just squaring the v, we're also squaring the 2. So what does that get us? That gets us 1/2 m4v squared. Let's move that 4 over so we can see everything a little bit more clearly. So what did we do to the kinetic energy if we doubled the velocity? We quadrupled the kinetic energy. We multiplied it by 4. So what about potential energy? Potential energy is kind of easy because there's no squares. So if we double the mass, same thing, we double the velocity. Double the height, also doubled. There's no squares in that equation, so there's no tricky business going on. What about the spring potential energy? Again, we've got a square, so we have to be a little bit more careful. If we double the distance compressed, so that's the x. So if we double x, we do 1/2 k 2x squared. That gets us 1/2 k 4x squared, which is, again, 4 times as much. So if we double the distance, we quadruple the the spring potential energy. And if we double the spring constant is not squared. So if we double the spring constant, we simply double the spring potential energy. What if we halved the distance that we had the spring compressed? What does that do? So if we take 1/2 k 1/2 x squared, all squared, we have to distribute the square, right? So we get 1/2 k 1/4 x squared. which is 1/4 of the initial energy that we had. Right? So if we have the distance compressed, if we divide that distance in half, it's not as compressed anymore, then we lessen the kinetic energy by 1/4. Now we finally get to talk about work. Work is simply a transfer of energy from one form to another form, and usually it's from mechanical energy into heat or into some other kind of energy that's a little harder to use. We can't use friction for energy very well. Now, in order for work to happen, there's two main things. First, the object must be moved. You can go outside and you can push against the school building all day long, and you'll get really tired at the end of the day, but you didn't do any work. You didn't move the building, so you didn't do any work. The other thing you have to do is some of the force that you've used in order to move your object must be in the same direction. So what are we talking about there? So imagine a waiter. A waiter has a large tray of food for you and your friends, and maybe it's your friend's birthday, so he's got a birthday cake. Right? As he's carrying the tray of food, which way is he moving that tray? Well, he's walking along with the tray, so he's moving this way. So he's moving it a distance this way. But which way is his hand putting force on that tray? Well, his hand is pushing the tray up. Those two, and remember, if we have something that is only vertical and something that is only horizontal, they don't care about each other. Anytime they're perpendicular, they do not interact with each other. So if we have something going straight up and something going sideways, it's like nothing happened. They don't notice each other. They have to be at least somewhat in the same direction. So how we calculate, so over here with our waiter, no work. He is not working according to physics. He's still getting paid according to everybody else, and he's working at his job, but according to physics, not working. So how do we calculate it? If all of our force and all of our direction are in the same direction, they're both horizontal or they're both vertical, you want to use work as the force used times the distance moved. But if not, if we have something at an angle, so if you are pulling a box with a rope and the rope is at an angle and you only pull the box this much, right? So you pull the box along the floor, you have to take the cosine to find the component of that force in this direction, in the horizontal direction. Now its unit is still joules. Pretty much this whole unit, our units are going to be joules. Work is a transfer of energy, it's a change of energy, so its unit is going to be the same unit as energy, which is joules, capital J. almost done. The work kinetic energy theorem says that the change in the kinetic energy of an object equals the net work done on that object. And sometimes we can even make it more general. We can make it the change of energy in general is the work done on the object. So our theme here for this one is whenever work is done, energy changes. So one example with the change for work is change in kinetic energy. So for example, if we have a car and it's moving and then it puts on the brakes and it stops, well, it slowed down and its kinetic energy changed because it went from moving, which has kinetic energy, to not moving. So that means some work was done. So we could calculate the work done by the change in the kinetic energy. How fast was it moving before? And since it came to a stop, all of that energy was turned into work. So there you go. Another example, one that's more general, where work is simply the change in energy, would be if you have a box and you push the box up the ramp, right? And let's say it's a frictionless ramp. That way we don't have to worry too much about that. But once you get up the ramp, you hold it still. It's not going to slide back down. You push it, it was still at the bottom. You push it up the ramp and you hold it up at the top of the ramp. That time it doesn't have any kinetic energy. There's no kinetic energy at the bottom. There's no kinetic energy at the top. But it did change gravitational potential energy because it came up above the floor. So anytime you go up above the floor, you're going to have an increase in potential energy, gravitational potential energy. So in this case, work is the change in energy in general and not just the change in kinetic energy. So last slide is just a summary slide. So it's got all of our equations that we've seen this time around. And notice we've got our symbols over here, right? I like to use EK, EG, EEL, work, but there's several other kinds of notations for energy that you may see. And all of them are measured in joules. And another thing to remember is that delta is final minus initial. So if it's delta x, that's the change in position, then it's the final position minus the initial position. In the case of energy, right, we see it over here. We have the delta and then EK, so it's the change in the kinetic energy. So it'd be the final kinetic energy minus the initial kinetic energy. And then one more thing, joules. I want to talk about joules before we get to anything else. Joules are another combined unit. And one way we can think of joules can come from newtons times meters. Right? If we take the unit for work, it's a newton times a meter, because the unit for force is a newton. The unit for distance is a meter. You can also think of it as, from this one here, you could think of it as kilograms times meters squared divided by seconds squared, right? Because we have velocity, which is meters per second. but we square it, so it's meter squared, second squared. Right? It's a lot of different combined units. But the reason I'm pointing this out is because everything needs to be in kilograms. And everything needs to be in meters. And everything needs to be in seconds in order for us to really have a joule. Right? So if we have a problem that gives us a mass in grams, we need to remember that it needs to be in kilograms. We have to do a conversion. If we see something that's in minutes or hours, we need to do the conversion to seconds. And if we see something in kilometers or, heaven forbid, inches, we need to get that into meters. All right, that's it for today. Next time around, we'll be talking a little bit about power.